Good day. So I like to. My name is Leon Takhtajan. I'm a chair of math department, and on the behalf of the math department, I like to welcome you all to the Blaine Fest. This is a fantastic event. So, like Blaine's 70th birthday, and we are all very proud to have such group of great geometers. So I think it's like the best group collected from all over the world, and we are looking forward to fantastic talks and great things to come. And so, before saying some other things, let me announce that there is a local organizing committee like Mike Anderson, who is the chair, then Marcus Curry, myself, there are the secretaries, and there is a local organizer, Paolo Lima, who, if you have any questions or anything, you please talk to him. Also, we appreciate and very grateful for the generous support from many sources, but in particular, it's a geometry conference, and we are very grateful to the Simons Center for Geometry and Physics for its support, and I'm very proud to introduce John Morgan, who will welcome you as well.
Well, I'd like to welcome all of you here. We're very happy to have this conference in honor of Blaine, a conference with a fantastic list of very interesting speakers that I'm personally looking forward to. So this is the Center for Geometry and Physics. We're always happy to have first-rate geometry and physics conferences here, so we're very happy with this one. One personal note. This occasion caused me to think about the first time that I met Blaine, which he probably doesn't remember because I was just a young pipsqueak at the time, very young. But it was in, I believe, the early 70s. It might have been the late 60s, but I think it was the early 70s. So this very dashing, handsome young mathematician from Berkeley shows up in a motorcycle jacket. I was incredibly impressed. What kind of math department do they have in Berkeley? Well, Blaine is still young, at least at heart. Dashing, well, you can judge for yourselves. But I haven't seen the motorcycle jacket in a long, long time. So with that, I welcome you again, and I'll turn things back over to Leon, will introduce our first speaker, I think.
Yeah. Let me introduce our first speaker. It's Aaron Naber, and he will from MIT, and his title is Classification of Tangent Cones and Lower Ricci Curvature.
Thank you very much. So for starters, I obviously want to thank the organizers for bringing me out to this event. Being the first speaker here, I feel I should share some sort of personal anecdote of Blaine, but I actually just met him my first time a week ago. So maybe I'll just more or less sum up our first meeting. Essentially, he came up to me and said, "It's very nice to meet you, Aaron. How about I pick you up at 1 and give you a tour of my house?" So he picked me up at 1 and gave me a tour of his house. That was my first meeting. Okay. So what I'm going to talk about today is those three. Roughly 2 papers that are both joint with Toby Colding. Before maybe getting into the specifics, I'll just sort of start with a general spiel about what this is all about. So, I mean, in our business, what do? We usually take some Riemannian manifold. I'm going to say pointed, so P is just some point in M. And we give it some sort of geometric conditions of some sort or another, right? There's half a dozen different things we can throw on this thing. It doesn't really matter. But for the sake of this talk, my geometric conditions will always be a lower Ricci bound and a lower volume bound. This is called non-collapsing. And what we ask is, what do our geometric conditions at hand say about this object? How can we control this guy geometrically based on our geometric assumptions? And actually, this talk is almost more about the converse. Knowing how to control such an object, we also want to know how can we not control such an object? In what ways can this thing be tremendously ugly with our geometrical constraints. It tells you what theorems can't be proved. So really that question comes down, actually both of these questions really, they come down to the following. They're easier to answer the following. Instead of studying one space with these conditions, usually you study sequences, limit spaces with these conditions. That is, you'll take some sequence, mi, gi, pi maybe, and they'll limit in some sense or another. And it turns out under the lower Ricci bound, the natural sense is always the Gromov-Hausdorff sense. So we look at some metric space limit. If we're not so familiar with this, it doesn't matter so much. What it is a way of taking a sequence of metric spaces and getting a new one out of it. And instead of asking how badly behaved or how nicely behaved is this guy, we might ask the same question about this guy. And really, I mean, first off, why is it the same question? I mean, why is this better? Because these guys can somehow look a lot worse than these guys, exactly because they don't have to be manifolds. They can have much more degenerate behavior. So somehow pointing out things that are fundamentally bad about this condition is much easier for something like this. Conversely, though, if we can say that these limit spaces, which a priori can look much worse, can't have certain behaviors, and there's nice contradiction arguments that tell us that these guys can't be so degenerate either. So it's the same thing to study these guys. Now, to study, actually, I'm going to change this to a y, I think, just to stick with my notes. OK. Now, to study these guys instead of these guys, why? I mean, general metric spaces or limit spaces in this kind differ from our fixed manifolds in basically one way, asymptotic behaviors. Locally speaking, these things can be much more degenerate than these guys. So to make this rigorous, let me just give a few definitions. This is going to be like our crash course in tangent cones for the next 5 minutes, and then I'll get on to new stuff. So rigorously, if we want to make sense of asymptotic behaviors of this guy, we define a tangent cone. Now to do this, let's first do the following. So if we pick any little y inside big Y and pick some r bigger than 0, then what? Then we define the metric space, which we'll denote as being big Y sub little yr. And all it is it's the same metric space topologically. The distance function is going to get rescaled by r inverse, and we're going to point by little y. Morally speaking, what just happened here, it's like saying that I took a little tiny ball of radius r around the point y. I rescaled it to a ball of radius 1. And so it's like saying that I used a microscope on this little region to zoom it up to a ball of radius 1. And then given that, we can define tangent cones by basically just saying what happens if we fix a point and we keep zooming up more and more by our microscope. It goes down infinitely far. What happens? Well, that's a tangent cone. So again, we say some metric space, which I'm denoting by y sub little y. So this is just some random metric space, is a tangent cone at little y if there exists some sequence r sub I going to 0 such that the sequence of metric spaces we have, by taking these little balls and zooming up, well, they converge to y sub little y. OK. So that's a tangent cone. Two trivial examples, just for those of us who are not so familiar with this, to keep in the back of our heads, and then we can call it that in terms of our crash course. First example, if y is an element of a smooth manifold M, then the tangent cone at y exists, is unique, and is always Rn. This is almost a weak way of saying that manifolds look locally Euclidean. This is actually a weaker statement than being a smooth manifold, really. But nonetheless, this holds. So at every point, we just look Rn. So this is exactly what I mean by having no sort of asymptotic structure, these guys. Or our second example can be the following. Take the ice cream cone. Big, giant, infinite ice cream cone. And now let's look at two tangent cones. We can look at y sub y. And let's say the vertex here is just y naught. Then we have two options. If y is not y naught, then again it's like Rn, smooth manifold. On the other hand, if y is y naught, then the tangent cone at this point is actually just itself. Because when I go zooming up on these little balls here and blowing them up, nothing happens. It's scale invariant here, right? So we got these two different behaviors. Okay. That'll be that. So we'll boil all this down to the following sort of questions. So question. What can we and can we not say about tangent cones of limit spaces under those assumptions? The point being that this was really the only way in which they differed from the smooth manifold, so this is what we should be studying. Okay. So let's begin with previously understood points, right? We're going to build ourselves up to something. So previously understood. Question? No. 1. If I take any point inside a limit space under these conditions, so there's a lower volume bound, that's actually not needed for this one, but that doesn't matter, and the lower Ricci bound, then tangent cones always exists. So picturing things like this is not so surprising, but if I throw a random metric space at you, there's no reason on earth that a tangent cone need actually exist at that point. There's no reason why we should be able to keep zooming up by a microscope and it should somehow stable out and stop changing so that we can get a limit. Unlike these examples up here, though,
does that mean given the sequence of Ri going to 0, there's a subsequence?
That's absolutely what it means, right? So this is Gromov compactness right here, result of that. So this is the lower Ricci bound really going on. Unlike these pretty pictures, they are not unique. There can be different sequences going to 0 where you zoom up and you get different things. Right? And I believe in the non-collapsed setting, so this lower volume bound, this really goes to Jeff and Cheeger. They had the first examples of such a thing. Unfortunate. And the final thing, and for us will be very important, is that tangent cones, the word cone is appropriate, it's a metric cone. What this means is that our any tangent cone, so y sub y, is the cone over some compact metric space X. Right, there's some other metric space. So like that picture there, I mean, we might want to call this the X in that context. So that y becomes the cone over X. You just picture exactly like an ice cream cone, but a different cross-section. And we call these X's the cross-sections. That's exactly what we call them. Okay. This most definitely also goes to Cheeger and Colding. There's a good deal of hard work, actually, in proving this sort of thing. OK, so this all being said, what I want to study in this talk is the following. I want to take a limit space. I want to pick some point, like P or Y or whatever I want to call it. And I want to study all the tangent cones that appear at that point. All right, so let's give this a definition. So our definition is as following. Given y in big Y, as in star, and I'm going to shove a star, so I don't have to rewrite all that nonsense every time. We define, I'm going to call it omega bar, sub big Y, little y. So omega bar sub y, little y, this is just some subset of the space of all compact metric spaces. Okay? It's just some subset of all of them with the property that some metric space, compact metric space X is inside this guy, if and only if the cone over it is a tangent cone at little y. So this is exactly the space of all cross sections. Everything in there, I mean, if you take a limit space, you take a y, this is the set of everything that can appear. There's some sequence going to 0, so if we go zooming up on it like this, we get exactly that guy there. Okay. Now, maybe a couple other basic points. I'm going to call a tangent cone smooth if this guy is smooth, the cross section is smooth. So like this ice cream cone up here, the way it's sort of drawn, it's a smooth tangent cone. Right? I mean, the whole space isn't smooth. There's a singular point right there. But the point is everything except the singular point is smooth. So we call that a smooth cross-section. Let's start with some elementary properties of this guy here. So what do we know about this subset here? We know 2 or 3 basic little points. Let's say that one, that as a subset of the space of all compact metric spaces, given the Gromov-Hausdorff topology, it's closed and actually compact. And the second is that it's actually path connected. I don't know exactly, but I would guess this goes back to Gromov. He did so many things like this, and I'm going to assume it was him. Okay. Okay, so now, everything we've done boils down to the question, what sort of subsets now? Well, we're looking at a limit space. We've now, at each point, maybe associated some subset of the compact metric spaces to it based on what tangent cones appear there. And we want to ask what sort of subsets can actually appear here. If you throw me a random subset of the space of all compact metric spaces and say, is there a limit space where precisely that arises as the space of tangent cones, is it true or not? So first, I mean, we're going to essentially answer that question for a class of these things in a few minutes. But let's write down some basic properties. In fact, let me write down what class first. So I'm going to make one technical restriction on the collection of subsets I'm considering. So definition. We call a subset omega bar inside this guy. Smoothly connected. If there exists a dense subset, so I'm going to say a dense path-connected subset, where each element of this dense subset is smooth. So it's an actual smooth Riemannian manifold. So we're saying it's smoothly connected if there's a dense connected subset of smooth guys. Okay? By no means does this mean that everything inside our subset is smooth. It just means there's some dense subset of it which is. Okay. Given that now, let me write down 3 more properties. These are the last collection of properties I'm going to write down, I promise, of what these guys have to satisfy. These are the important ones in some sense. So less elementary properties. Some of them aren't so bad, actually, of the collection of all tangent cones at a point for a limit space with a non-collapsed and a lower Ricci bound. So I'm going to actually give these names, P1, P2, P3. P1. So if we have 2 elements of it. So we have two possible cross sections. And the volume of these two guys are actually equal. So technically speaking, these are all n-dimensional spaces. By volume, I mean n-1 dimensional Hausdorff measure. But if you like, I mean, we may as well assume these are two smooth elements. It doesn't matter. That's easy pictorially anyway. So volume is volume. We know what that means. So their volumes have to be the same. If you have two different guys inside the subset, then they have to have the same volume. The second property is that if you have some guy in here, again, for simplicity's sake, I'm going to assume it's a smooth element, but that's not actually necessary. Then its Ricci curvature is bounded below by n-2. So cross sections have to have a lot of Ricci curvature. Now the third condition, which I'm going to be a little vague about because it's the actual technical one, if you have some element of it, then X is, I'm going to call it geometrically trivially cobordant. Okay. So I'm not going to say exactly what that is, but I'll give you a feel for what that is. So if this is supposed to arise as a possible tangent cone, then that's roughly saying, I mean, let's just use this picture here. That's roughly saying that we have a limit of smooth guys, which looks like this with the cross section. Now, what that should mean, like for instance, let's say that this is some smooth element, just for simplicity's sake. Then there are actually nice theorems here that, I mean, you can certainly even picture it this way anyway. I mean, you can picture your smooth guys as being, say, diffeomorphic to this and this annulus here anyway. So now what you've got is this closed guy, but if you cut it off here, it's smooth closed manifold, where if you cut it off here, it's got boundary X. So certainly it's got to be cobordantly trivial, right? But there's a little bit more of a statement here in the sense that this is a cobordism, which isn't just a cobordism, but it's something that has lower Ricci bounds and actually looks kind of conical at infinity. So that's what I mean by a geometrical trivial cobordism. But in particular, it's certainly got to be trivially cobordant for something like this to actually happen. Okay, so fine. We've gone through all this nonsense. We've defined what the space of all tangent cones at a point is. We've given them three properties. We know these are necessary conditions, right? And then the question is, if we are throwing a random subset of the space of all metric spaces, and maybe it satisfies all three of these conditions, is that sufficient? Is there a limit space that actually has those as the space of tangent cones? And actually, I mean, as long as it's smoothly connected, the answer is yes. So it's actually sufficient. So let me try to make this precise. So the exact theorem is the following. So the theorem is that, let's take some subset, the space of all compact metric spaces, which is smoothly connected. So it's just got a dense subset, which is smooth. And let it satisfy P1 and P2. And actually, for technical reasons, it turns out you only have to assume a single element satisfies P3. And if that condition is confusing, this is the one you can ignore. then the statement is that there actually exists a limit space. So that is a sequence of Riemannian manifolds, pointed, which satisfy, in fact, you can even assume it doesn't really matter, as it turns out. They can all have non-negative Ricci curvature. It doesn't really matter. And some distinct lower volume bound. Such that the space of tangent cones at this point is exactly this thing. So in our terminology, that means this. Okay. So that is, we take some subset of the compact metric spaces. They satisfy our necessary conditions to arise the space of tangent cones at a point, and actually it's sufficient. There is such a, if you have such a subset, there is such a limit. Okay. Now, that's all fine. But really, I mean, the point of such a theorem is really to build new examples. It's to use this to construct new limit spaces that basically look as horrible as possible. We want limit spaces that have as little nice behaviors as we can get away with. If for no other reason, then this is telling us what it is that we can and cannot expect to actually hold in terms of structure theorems. So the rest of my talk will be spent giving various applications of this, and then going through a little bit the proof. Okay. Each example will probably get a little bit more complicated than the last. So let's just start with one. So the first example is the following. Let's just maybe start with some small two-sphere, right? It's like a two-sphere, but it's maybe tiny. You know, it's smaller than the standard two-sphere. So pictorially, we visualize it like this, give or take. I don't know why I just said that. I just drew something random. So we have a nice little sphere. Certainly, it satisfies, I mean, it's got some volume, whatever. It's got a lot of Ricci curvature as long as it's small. And let me actually, I mean, for the sake of actually explaining this condition a little bit, let me show actually that this thing actually satisfies the geometrically coordinate condition, even though I was a little vague about what that means. So it's supposed to be a coordinatism which is geometrically trivial. Well, here's my cone. Take the cone over this guy. It kind of looks like this thing here. Well, the point is certainly this is coordinately trivial because we can take this guy and smooth it out. And the point is that we can do this in such a way where this thing still has non-negative Ricci curvature. In fact, non-negative sectional curvature. It's really nice here. The smoothing is very clean. So that actually, you can take that almost as basically being the definition of geometrically coordinately trivial as far as we're concerned. So there exists a space like this. So what that means is that if I take any family of metrics on the two-sphere with the same volume and a lot of Ricci curvature, then there has to be a limit space that has all of these as tangent cones. So in particular, let's think about the following sort of family. Here's sort of one nice metric on the two-sphere. Maybe another one down here is like this. So it's like we have a European football up here and an American football down here, and we can certainly sort of visualize going between the two. Right? We just sort of start rounding off those corners somewhat. And we can do this in such a way where, I mean, in fact, the Ricci curvature of these singular points is just basically becoming more and more positive, so this is no big deal. And, you know, you normalize some nonsense, and you can make sure how they all have the same volume. So they satisfy the constraints of the condition. So strictly speaking, what I actually want this thing here to be is the suspension, call it suspension, over some circle, something like that, of small radius. Okay. What that means is that there has to be a limit space for which all of these guys appear as tangent cones. In particular, the following two things appear as tangent cones. This appears as a tangent cone, or just nice ice cream cone. And the cone over this appears. But the cone over the suspension of something is actually just R across it. So this guy here is like just the cone over S2. And this here is actually like R across the cone over S1. So this is a sequence of 3 manifolds now. Which will limit to my limit space y, so that the tangent cones at y include this guy and this guy in particular. And this has 2 interesting new properties. First off, it's actually the first example of a 3-dimensional limit space with non-unique tangent cones. Roughly speaking, this is because usually the way these things are constructed is by having a lot of dimensions, so there can be a lot of curvature to sort of squeeze out of other places. Usually there's a lot of symmetry assumed to sort of force these things. Much more interesting, actually, is that's the first example where one tangent cone is smooth, so the cross-section is smooth, and one is not. It's r cross something. So I'll elaborate on that point in a second, but maybe I'll generalize this example in just 2 or 3 words to one other, and then I'll say goodbye. One can complicate this up a little bit more without it being too much. I could have just started with this following example, but I felt it was easier to do this first. Start with an n-1 sphere, which is maybe very small. And we can do the exact same thing now, where, so this is sort of like our n-1 sphere. And we can have one family. So the family can be much bigger than just a line sort of sequence. We can have one thing that goes to a suspension. So again, it's like a football. Oh, we can also have one that goes to the suspension over the suspension of something over a sphere of dimension. So this is like Sn-1. This is like the suspension over Sn-2. We can go to the suspension over the suspension of Sn-3. So this gets a little tricky to draw at this point. Oh, wow, that's really bad. Pictorially, there's not, so this has 2 singular points. This guy has a whole circle of singular points. So this is like a flying saucer. In fact, I think it's better to picture this. Picture this as a flying saucer and you're fine. This is the suspension squared of Sn-3. And so forth and so on. We can make as many suspensions as we want. Suspension to the k of s to the n minus, so what was the formula? 1 minus k, I guess. So we can make as many of them as we want appearing. So all these guys will appear as tangent cones. So what does that mean? That means we have a limit space of some dimension now, whereas the space of tangent cones includes Rn to the k cross the cone over something smooth, which is some sphere of n minus k minus 1, actually, but it doesn't really matter, for every k between 0 and n minus 2. Who cares? The point is that you can't stratify. You can't look at a limit space with a lower Ricci bound and try to split points up based on how many RK factors split. This is normally how you stratify a space. And the point is this has no meaning now because at a single point you can split as many factors or as few as you want. It's not preserved by the tangent cones anymore. You can split lots or very few. So stratifications have no meaning in that sense. The strong stratifications have no meaning. Usually, I mean, the way this is done is almost like that. I mean, but stratifications in these sort of weak contexts are usually done in a double negative. I mean, you can stratify, but usually you stratify sort of based on, it's more or less what you just said, based on the highest dimensional tangent cone RK factor that doesn't split. So that you can get a stratification, but you usually, I mean, you phrase it in a slightly funky fashion. So that possibly lots of things could split, but maybe past some point you don't get higher splittings, something like that. Okay. Okay, things actually get more complicated now. So the next example is, I mean, maybe I'll just sort of say it in words first. So what we want to do now is build an example of a limit space where we have some point and we look at the space of tangent cones, and there are going to be two tangent cones which are not just not isometric, they're not homeomorphic. So we want to see that homeomorphism classes are not preserved by tangent cones. The easiest way to actually do this first is just to write this down as a general theorem and then to go from there. So the basic theorem is this. There exists a sequence there are actually 5 manifolds. With the usual assumptions. Oh, good, I didn't erase them. Did I? No, I did not. So they all have, we can even say non-negative Ricci curvature, and they have a distinct lower volume bound, so they're not collapsing. Such that the following holds, such that there exists distinct tangent cones I'll call this C of x naught and C of x1 at y, so at little y, where, let's say, x1 first. x1 is homeomorphic to S4, and x naught is homeomorphic to CP2 connect some CP2 bar. Okay. Conjecturally, all right. The conjecture being based on trying very hard to build one in dimension 4 and not being able to do it. So more specifically, the conjecture would be for any limit space away from a set of Hausdorff codimension 5, you should have homeomorphic tangent cones. Okay, so I'm not going to describe line by line how to build this. I'm just going to give you the basic morals, because after that, what you've got is a lot of pages of computations, and I'll make it a homework assignment. So what do we need to actually do this? So need. I erased my conditions. Oh well. We're going to want a smooth family of metrics, Riemannian manifolds. On CP2 connect some CP2 bar. Parameterized by some S, say, where S is inside 0 to 1. Such that the following conditions hold for all these guys. So that 1, the Ricci curvature of all these guys should be bigger than or equal to 3. And the volume of all these guys, volumes of S, just doesn't depend on S. So they all have to have a lot of Ricci curvature and constant volume. The second condition is that CP2 connects some CP2 bar with the G sub 0 metric, I'm going to say, is supposed to be geometrically cobordantly trivial. So it's in particular, this is maybe a first guess as to why we pick CP2 connect some CP2 bar. It's at least, I mean, it is trivial cobordant, right? So there's maybe some hope of building one with a good geometry. And the third condition is that in the Gromov-Hausdorff sense, if we look at these sequence of metric spaces as S goes to 1, then they should converge in the Gromov-Hausdorff sense to S4 with some metric. If all those three things are satisfied, we can apply the main theorem, and you get a limit space, which will have all these things appearing at tangent cones. In particular, most of them are CP2 connect some CP2 bars, and at least one of them is this guy over S4. And so that's a claim. OK, so let me just sort of wave my hands and draw some pictures. So let's actually start with, OK, so I mean, in terms of my moral outline, I'm going to ignore condition 1 more or less entirely, and you're going to believe it's true. And then let me start with condition 3, sort of how this should look. So the point is now I want to visualize CP2 connect some CP2 bar as being essentially 2 copies where you have an S2 with some vector bundle over S2, and you glue them together along the boundary. Right? So sort of pictorially, we have something like this. And they sort of get glued together along the boundary. So that's CP2 connect some CP2 bar. And now I want to say that you can actually put a nice warped product metric on this guy to give this thing a lot of Ricci curvature as claimed, and that you can do it in the following way. You can do it in a way where as S goes to 1, what you're going to do is you're going to basically take these two spheres and sort of crunch them to a point, so that near this region, you should just sort of hope anyway that all that's happening is you're adding a lot of positive curvature to it, so that as S goes to 1, S can be like roughly visualized as, say, the diameter of this thing. 1 minus the diameter, I suppose, of this thing. Then what should be happening is it should be going to something like this. So again, we're staring at sort of like the football picture. So once we take all this topology and squeeze it out, we just have an S4. G0, on the other hand, the way we're going to picture that is sort of different. Instead of viewing CP2 connect some CP2 bar as being the gluing of 2 vector bundles over S2, we're going to picture it as being a twisted 2-sphere bundle over S2. And this is sort of the standard picture you want anyway to sort of build a cobordism. So what we're going to do basically is just say that, OK, G0 should be a nice metric. It should respect this fibration, a fiber bundle in a nice way, so that essentially we're going to replace all the S2s by B3s, just sort of close up those S2s like that, and again put a nice warped product structure on it so that it'll have non-negative Ricci curvature. So it'll give us some 5 manifold with non-negative Ricci curvature, and it should, on the boundary, look like CP2 connect some CP2 bar. So this is sort of our geometrically cobordantly trivial condition. And now all I'm going to do is say is that now you have to get from this metric to this metric while satisfying this. And I'm not going to bother with explaining that because it's just a mess. And doesn't give any intuitive feel for anything. It's just more of the same. OK. I have one more example to talk about, but I'm going to probably just do this in words because I don't have enough time to talk about the example and actually go through the proof at least a little bit. So my last example that I kind of want to discuss is the following. So it's related to, it actually requires a generalization anyway of this main theorem. Actually, it's a generalization, but it's what you actually prove. And it's about studying Reifenberg spaces. So roughly what that means is we want to consider limit spaces for a second. Where in some sense we want to build something that's as close to looking like a manifold as possible without being one. right? So we want to say that in every nice sense, it looks like a manifold, and that if this were a nicer situation, you had more than just a lower Ricci bound, you can prove it is a manifold. But we want to see somehow, geometrically, so a Riemannian manifold, but we want to build something on this so it's not. So in fact, actually, what we're going to have this do is these guys will just converge to, I'm going to say, make this example simple. It's just going to be Rn with some random metric that is not the standard one. The base point can be at the origin. So homeomorphically, it is going to be a manifold. The tangent cone at every single point of this limit space is Rn. So this is what I mean by a Reifenberg space in a sense. So it looks homeomorphically like Rn, and geometrically, it looks like Rn when you zoom down. It looks like a Riemannian manifold. Now, although I'm kind of assuming it somewhat anyway by the way it's being written, it was actually proved by Chigger and Colding that under such a situation, it's automatic that this thing is going to be bipolar to a Riemannian manifold. So essentially that means that this distance function here can only be Holder away from the standard one in a certain sense. So it is close to being one. It was asked whether or not it can be by Lipschitz to the thing. And although it was probably expected notwards, of course you could ask otherwise. Could it be C1 alpha close to the thing? So forth and so on. What's the maximum cap there? So what this limit space is going to do is basically the following. It will not be C1 alpha close to Rn, but it will be not so for sort of trivial reasons because it'll have horrible properties besides this. It will be by Lipschitz embeddable into a higher dimensional Euclidean space. So we could basically prove that all such limit spaces are actually by Lipschitz embeddable. So we have some Lipschitz structure on it, but it's not quite what they were asking. But what's going to happen is the following. The notion of angle at this point is going to be awful. So let me explain this. So given 3 points, this can be in any, space, but this can, I don't want to say Rn because I don't want it to be confusing as if I'm using Rn, so let's just say in Y. We can define their angle. So this is sort of the standard Alexandrov type definition that you do for lower sectional curvature by the following sort of annoying formula. So you actually define the cosine of the angle, as I recall. By this formula. And then given that, what you can do is you can define the angle between two g at Essex coming out of a point. So you take a point. This can maybe be 0 in our picture here. We look at any two g at Essex, gamma 1, gamma 2, minimizing g at Essex. And you can try to define their angle by simply looking at the g at Essex, the angle between the 3 points you get by evaluating these things at time t and taking a limit. So the would-be angle that you want here is so I'm putting this in quotes because we're not sure the limit exists. But the limit as t goes to 0 of the angle between gamma 1 of t 0, because that's where they're starting, and gamma 2 of t. OK. So the question was, does this make sense, say, at least on a Reifenberg space? Does it make sense in a situation where you look as close to being a Riemannian manifold as possible? Can you define the angle between two minimizing g at Essex coming out? And here's the basic property I'll just sort of say in words that this limit space has. So if you look at this point, you pick any two other points you want, and you look at the minimizing g at Essex connecting them. So that's say you look at any two minimizing g at Essex coming out of this point, doesn't matter which two, and you pick any angle between 0 and pi, any at all. So any two g at Essex, any angle. Then there's a sequence of ti going to 0, so that this guy converges exactly to that angle. So not only is angle ill-defined, for every 2g at Essex and every angle, it appears as a possibility if you take the limit. So it's about as bad as possible, at one point anyway. So anyway, no, angles can't be defined for Reifenberg spaces. OK. roughly speaking, the way you build this space is that your cross sections, just like before, you have to build this family of cross sections. They're all the sphere. They're all the n-1 sphere, but you change them. By volume preserving diffeomorphisms. So it's like you fix the like isometrically, they're all the same, but you let them sort of change in coordinates by awful things. And then what sort of appears here is something whose every tangent cone has to be Rn, but they're sort of different Rn's. They don't agree with each other in a certain sense of the word. Okay, so in my last 5 or 6 or 7 minutes, I'm going to say the proof of main theorem. So did I erase the main theorem? That's rather unfortunate. Beautiful. OK. So vaguely speaking, how do we prove this? OK, so what I'm going to do is actually ignore the P3 condition. I'm going to kind of tell you how to construct the limit space. And then the fact that it comes from a sequence of smooth things is basically where the P3 condition comes in. So let's just talk about constructing the possible limit space. So what we're going to do is the following. So notice that if there's a dense subset of this guy where they're all smooth and they're connected, then there's this dense subset of this guy where they're all diffeomorphic. Right? So really, they're all sort of like all the pictures we had here basically had a fixed space with smooth geometries varying to things that were outside that space. That it sort of always has to look like that based on this, if that's going to hold. So that is, we have, let X be a smooth compact space with X G sub S. So this is a family of metrics on it. Be dense and gamma bar. So being a dense subset that's smooth and smoothly connected, the point is that you can actually get a curve of smooth guys that actually is dense inside this guy. So that's the first key point. So we can just keep varying around this whole thing, like all the pictures we've been drawing so far, of sort of one fixed guy with some smooth geometries that are dense inside this. OK. Let's note 2 things. First, we can change, once we have some dense curve of geometries inside this, we can change it by a reparameterization to insist on the following. So this is really nothing at all to make this assumption. dt of, so the rate of change of the metrics and their second rates of change and the covariant derivatives of the rates of change. We could actually keep going if we wanted, but we'll stop there. Are all bounded above by 1 in norm. Norm being with respect to G sub t. So the point is you can actually construct this right away just by meddling with what it means. OK. Now, we're going to choose a metric on the cone over X. So this is what the limit space is supposed to look like. So G bar will be the metric on there, and it's going to look like dr squared plus r squared h squared of r, g of f of r. So notice that if there was no h and this was just some fixed something, that's exactly what a metric cone is. Right? So if I fixed a g, then that there would be that. So that's like saying it's a perturbation from a metric cone here, with these 2 functions being my perturbation functions. And let's note that G sub s is G of s in the picture above. And just so this is changing how I'm actually going through this thing. Thank you. A line, definitely a line. Because it's supposed to be dense. It couldn't be dense if it were a compact subset of the thing. Unless there wasn't much to it anyway. OK. And in fact, I'm going to tell you what H and F are explicitly. This guy should be like close to 1 and converging to 1 if you're picturing this as a perturbation of a metric cone. And this should be just something that goes to infinity as R goes to infinity, or as R goes to 0, really, I guess. And let me say where F and H are given by. So here's sort of the rather aggravating formulas. So E and R naught are constants here. And capital F is also a constant. Okay. So H is 1 minus E over the natural log of the natural log of R, and F is some constant times the natural log of the natural log of the natural log of R. Morally speaking, what this is saying is that this is converging to 1 at some rate, but this is converging to infinity at a much slower rate as R goes to 0. That's the moral there, and this is why you need a whole bunch of logs to make it work. Okay. And the basic claim is that if I pick E, R naught, and F correctly, this thing has non-negative Ricci curvature. I mean, the only statement I'll really make about this, oh, hey, I missed something up here. There's one really important thing here that I skipped. So this condition holds, and the volume forms of these guys are independent of T. So the point is that if these things all had constant volume, remember that was an important assumption, you can change them by a diffeomorphism to make them have constant volume form. This is a really great theorem by someone I forget. It starts with an M. Thank you. So we can assume these all have constant volume form. And my basic claim here is that if you compute the Ricci curvature of this guy, there's a notebook of nonsense behind finding this formula, then everything will be positive. All the terms will be really positive, with the exception of, well, and there'll be some negatives that are not so bad, and then there'll be some negatives that are really awful. But the really negative awfuls all come in the form of derivatives of this thing. So that if you basically make it a constant, they go away, you're done. Okay, so that was my 5-minute or less version of the proof. I'm done.
Questions, please.
So is the tangent cone of Einstein manifold unique or not?
Say that?
Consider the Einstein manifold, is the tangent cone of Einstein manifold unique or not?
Under the lower Ricci condition, no. Not under a lower Ricci condition. I mean, under an Einstein condition, I mean, if it's smooth, yes, but if it's not smooth, then that's not clear. So under lower Ricci, things are highly non-unique.
Questions?
So do these Reichenberg spaces have tangent cones with any new interesting properties? It seems like
the tangent cones, by definition of being a Reichenberg space, the tangent cones always are in, and actually even conversion to Rn at a definite rate everywhere. So the whole point is that the point of a Reichenberg space is that it's supposed to look as close to being a Riemannian manifold without being one.
But it has no conformal structures.
I have no idea what other structure it has.
So maybe back to my question before. Do you need this to be dense with sort of cycling around here?
Yeah.
Because otherwise it's not going to converge.
I can
I'm picturing when R goes to 0.
No. As R goes to infinity, it has to keep going around. This can, so yeah.
It's sort of cycling.
No. So,
Okay.
wait, so 0 doesn't matter. I mean, R can be, and this can be that, right? It's as it goes to infinity. This is what you're asking, right?
The main thing is that you want subsequences to go to all the different possible limits.
That's right.
So it has to be coming back. It can't just be.
Yeah, absolutely. Yeah. Yeah, that's why it has to be dense, right? I mean, every point either it gets, it has to, you're saying it has to.
Infinitely often.
Yeah, that's right. It comes infinitely often to every point. That's true. I mean, as long as it's not compact and this is a one-dimensional set that's moving smoothly, that kind of has to be the case. And if it's one-dimensional, then it is, I guess as long as it doesn't stop.
Other questions? Okay, let's thank the speaker again.